AQP knows how to compile and build a parser from, and transform it into executable code. So here's the expression. So an expression consists of an integer, an add operation, another integer. And every rule that exists in the grammar can have a corresponding rule or a corresponding method called an action method that is in another class. And the action method is invoked automatically at the end of the rule as we're doing a parse, and it says how to transform whatever we just parsed into its equivalent abstract syntax tree, where an abstract syntax tree describes how it's to be solved. So for the expression rule here, when we get to the end of the expression, this method in the actions automatically gets invoked. We know that this one gets invoked because it has the same name. And it gets passed as a parameter whatever we just matched, and that goes into $slash. $slash in Perl 6 is the match object. Whenever you do a regular expression match, the result goes into $slash. And inside of this method, we now say, what kind of a pair op did we get? The add operator, which corresponds to whatever got parsed here. If it's a minus sign, then our operation is going to be sub. That's the parent operation for doing subtraction. Otherwise, it's going to be an add, which is what we would do for an addition. If you're wondering about the question, bang, bang, that's the same as the Perl 5 question mark colon syntax. It's the ternary operator. So we first of all figure out what kind of operations we're going to perform, and then we create a new opcode node, a new operation node in the abstract syntax tree that has the operation we want to perform. It has the value of the first integer that we parsed and the value of the second integer that we parsed. So this is going to take two integers and either add or subtract them, and that's the result. Yes?
What does make mean?
Make, good question. Make says that for whatever parse node we're at, we're going to associate this abstract syntax tree with that parse node. So every,
we are just replacing that node with this? Or?
No, it's an attribute of the current node.
Oh.
So that every parse node also knows its abstract syntax equivalent. Yes.
Why are the plus signs necessarily?
Because otherwise they would be strings. Because actually they'd be match objects. They'd be whatever we match for the integer. So the plus sign says converted to a numeric value. So my abstract syntax tree node is actually going to hold a constant integer value here and a constant integer value there. I'm just computing it in composite. Okay, so back to the original. This is what the full thing looks like. So again, for the top, that's the top rule for the entire program. I simply take whatever abstract syntax tree I got for the expression and put a block around it so it's an executable piece of code. And that does that. And the last piece I need is a compiler object. So I have my grammar that does the parsing. I have the abstract syntax, the action methods that say how to convert a parse tree to an abstract syntax tree. And I have a compiler that controls the whole thing. So for my compiler, ABC compiler is a high-level language compiler. This way I just inherit a bunch of methods that already exist. And I tell it the language I'm doing is ABC. My parsing grammar is this particular grammar. The actions for transforming is this particular set of actions. My mainline code is I'll grab the arguments from parrot. That's kind of a nasty thing I'd like to get rid of someday, but I don't know how to do that yet. And I'll call my compiler that I just initialized up here, pass it the arguments from the command line, and I'm done. I've written the compiler. So let's see it work.
So that class is an instance?
In Perl 6 classes, when you declare a class, you get a type object, and the type object is an instance. So I'm just working on the type object directly. So running the program gives you that. You can never trust a slide live demo. I love live demos. I love them when they blow up too. So here we go. abc-1.pm. This is just to prove that the program that I'm showing you is actually the real program. I didn't like shift anything in between there.
Yeah, I was thinking we've seen that
we have a version of IO prompter written for Perl 6, but it doesn't yet do all the other stuff. That is going to be one of my next tricks because I'm tired of typing all this stuff in. Okay, so I'm just going to run AQP on that program, and since it gives me a prompt because it's asking me to type, it's got an automatic REPL built in, read, evaluate, print loop. So now I'm going to type in a valid program for this language, plus 4, and it should come back with 7. So I just wrote a compiler to add numbers together. If I give it something that it doesn't recognize, like that, it tells me unable to parse source. I can make it smarter, so it tells me where it was unable to parse it, but it was unable to parse it without knowing. The default high-level language compiler object gives you lots of options so you can figure out what's going on. So if I want to see what the parse tree looks like, I can just add target equals parse to my program. And so now I've got a compiler, but instead of running the program, it's just going to stop after the parsing phase and show me what it parsed. So if I do 3 plus 4, that's the parse tree. So when I did 3 plus 4, it parsed it out. We know that we were looking for an expression that's here. Inside of the expression, we have an add-op and 2 integers that were parsed. The add-op that we got is a plus, and the 2 integers were the 3 and the 4. If we want to actually see the abstract syntax tree, that's just a different command. So I'll say, show me the abstract syntax tree for whatever program it's entered. So I can do 3 plus 4. And that shows me the abstract syntax tree that was created from my source input. So here we have 3 plus 4 is my source. I have an abstract syntax tree where the outer node is a block. It contains one child that is an operation. That operation has a pure opcode of add, and its 2 arguments were 3 and 4. And if you really are wanting to debug your program, then there's a target pure option that shows you the parrot pure code that got generated for that particular program, and it looks like that. So 3 plus 4 ended up resulting in creating a block. Here it's anonymous. It had in it that we created an integer. We gave that integer the value of 3. We added to that integer the value of 4, stuck that in a new PMC register, and returned that result. So that's all there is to creating a compiler using the QP. Now here are my slides in case the light demo broke. Okay, any questions so far? I'm going to do a more advanced example in a second.
How did this work with code generation? Because it's so short.
Once you have it to an abstract syntax tree, the toolkit knows how to go the rest of the way to peer and executable.
That's fine.
Yes, I didn't make that clear. So the compiler toolkit says you get it as far as an abstract syntax tree, and it does the rest.
Right.
Yes.
So to clarify that, if in terms of compiler, this is a front end to a compiler that performs intermediate representation.
Yes.
So the toolkit is a back end, and the
Yes.
back end parrot.
Yes. And someday we hope to have other backends.
Which means the classic one of bootstrapping to another platform. You have a back end, you have a cross compiler.
Yes.
You cross compile. Yeah.
Yes.
Sweet.
And it's self-hosting. NQP is self-hosting. So once we have that backend, I can actually make NQP native on the remote platform, and that remote platform will then have Perl 6 regular expressions.
Everybody gets expressions.
Yes.
Whether they like it or not.
Okay, so yes, there's a backend that goes all the way to the generation. So there are some built-in classes that come available with NQP. One of them is HLL grammar. This is a default grammar for writing high-level languages. And there are some built-in rules. So you don't have to worry about writing these rules yourself. You could just inherit from HLL grammar. There's an operator precedence parser, which I will talk about in more detail in a second. But what you just saw in that example is an example of top-down parsing. For expressions, that's very, very slow. So we'd like to have something that can do bottom-up parsing, and this expression rule automatically takes care of that for you. There's a rule for handling white space and comments. Parsing integers and parsing numbers is very common among high-level languages, so there's some default rules to do that. How many people like writing regular expressions to parse floating point numbers? Right? You get one for free. That number will handle floating point numbers in the standard ones that you would expect. Same thing for handling strings with backslash escapes of various forms. You get one of those for free from the HLL grammar for being able to handle backslash escapes, including the fancy ones like backslash x with the digits or backslash c, things like that. So if you're writing a compiler, a lot of the tokens are already in place for you. You can override them, but as you're starting, you can just use the ones that are there. So it allows you to prototype languages very, very quickly. So here's an example of a compiler where we're going to use operator precedence parsing. And this time we're going to go we're still just doing expressions, but our expressions are going to be much more complex than what we had before, and we'll deal with precedence. So we're still doing the same thing where I'm parsing an expression, but now I'm going to make use of the expression rule that came from HLL grammar. So it already knows how to parse expressions in a big way, but it doesn't know the tokens. It's blank in terms of the actual tokens that it understands. And so you define those. So my values here are going to be terms, are going to be integers. It knows how to parse parentheses. It knows the unary minus operator, and it will know multiplication, division, addition, and subtraction. Now, in looking at these rule definitions here, you'll notice that my names got a lot more complex. And this is what a proto-regex is. A proto-regex is like a multi-method, but for regexes. In other words, I can have multiple regexes, all that have the same identifier, and when I try to match, it tries to match all of them in parallel and picks which one is the best match. So here, what I'm doing is I'm saying that this is an infix token, which means it's an operator that will occur between two operands. And the actual text of the token is a star. And the fact that it comes between two operands, that's what the operator precedence parser is going to handle for me. So whenever it comes to a point that it says, I'm looking for an infix operator, it has a rule that says, match an infix operator at this point. And all the possible infixes will then be tried, and whichever one matches is the one that will come out and be used. So this will match an infix asterisk, an infix slash, an infix plus sign, and an infix minus sign. Immediately after that, I have this O notation. And what this does is it tells me two things. It tells me what the precedence is of that operator and what opcode to use when that operator is encountered. So the precedence here, you can see that multiplication and division have higher precedence than addition and subtraction. And the unary minus has higher precedence than any of those. And so it automatically knows how to deal with those things. Unary minus is a prefix operator, and so we tell it that it only has one operator, and so forth. So that's the parser for a much more complex expression language. Let me see what the next slide is here. Oh, and then these are the corresponding actions. So for this one, it's really simple because most of the actions I get by default by specifying PROP. If PROP is specified, then the expression parser already knows how to turn that into the appropriate abstract syntax tree node for that particular operation. And so for all of these, I don't have to specify actions for them. I can if I want to, but I don't have to because it's taken care of by this part. The only thing I need to specify how to create abstract syntax tree nodes for are for the value and for handling the circumfix operation, the surrounding parents. So I have this one here for whenever I parse a value, then I want to get the integer value from whatever integer I parsed. And that's came from the previous one. And if I get circumfix parents, because I'm putting the parentheses there to enforce precedence on an operation, then I'm just going to take whatever result is inside of the parent. And if we go back, we can see it's recursive here. That whenever I parse a parent, I go and get an expression inside of that and get a closed parent. That gives that a higher precedence than the things surrounding it. And that's it. That's all I have to write. Those two things and my compiler code. So live demo again. Okay, that's the right thing. Let's get out this here. And let's look at again, this should be the same code that I had on the slide. And again, I just have the compiler do the same thing as before. Let's try running it. And so now, instead of just being able to handle addition and subtraction, I should be able to do something a bit more complex. So let's do 3 plus 4 times 5 should be 23. Just to show that it actually gets the precedence right. Even if you switch the operands, multiplication is higher than the addition, and so on. And we can do the same sorts of things that I did earlier. We want to see the parse tree, 3 plus 4 times 5.